Can a single line be folded into a one-dimensional universe? The answer is yes. But after scientists worked out the math, they fell silent for an entire decade. Because what they had discovered seemed to point to something deeply unsettling. The universe we live in might not be truly three-dimensional at all. In 1890, the mathematician Giuseppe Peano did something that looked almost casual. He drew a square on a sheet of paper, divided it into 9 smaller squares, and then used a single line to pass through the center of every little square. After that, he divided each of those smaller squares into 9 more pieces, connected them again, divided them again, and connected them again. Over and over, endlessly. On what seemed like an ordinary, almost meaningless afternoon, Peano drew a line that would overturn the way humans understood space. It became known as the Peano curve. In theory, after infinitely many steps, this line could fill every corner of the square. And that raised a question no one could easily answer. How can a line become a surface? The question stunned the entire mathematical world. A year later, the great mathematician David Hilbert created something similar. His version was more orderly, more elegant, but the conclusion was just as absurd. After being folded infinitely many times, a single line could perfectly fill an entire two-dimensional plane. At the time, the reaction from mathematicians was not excitement. It was fear, because according to everything people believed about dimensions, this should not have been possible. Back then, the idea of dimensions seemed simple and obvious. A point was zero-dimensional. A line was one-dimensional. A surface was two-dimensional. A solid object was three-dimensional. No matter how much a line twisted, it was still supposed to be a line. No matter how you cut a surface, it was still supposed to be a surface. Dimension was like an invisible wall, clearly separating different worlds from one another. No one had imagined that this wall could be cracked open by a single line folded infinitely upon itself. One dimension was one dimension. Two dimensions were two dimensions. There should have been no strange territory in between. But now, these two cursed curves had torn open a hidden crack between the integer dimensions, a crack no one had ever thought to question. Then, in 1904, mathematician Helga von Koch took a simple line segment and divided it into 3 equal parts. On the middle section, he built an outward-pointing equilateral triangle. Then he removed the original middle segment. What remained were 4 smaller segments. After that, he applied the same operation to each of those segments, again and again, forever. The final shape looks like a snowflake from a distance. Zoom in, and it still looks like a snowflake. Zoom in again, and the pattern is still there. No matter how far you magnify it, it never truly smooths out. This is the Koch curve, a fractal, and one of the most famous mathematical monsters in history. What makes it even stranger is what happens if you turn it into a snowflake. With every step, its boundary becomes longer. The first step makes it longer. The second step makes it longer again. The third step keeps stretching it further. If the process continues forever, its perimeter eventually tends toward infinity. And yet the area enclosed by it does not grow without limit. Instead, it gradually approaches a fixed value. In other words, this snowflake has an infinitely long boundary, but it occupies only a finite amount of space. But even that is not the part that truly makes your scalp tingle. The real shock came when mathematicians calculated the dimension of the Koch curve. It was not one-dimensional. It was not two-dimensional either. Its dimension was 1.26. What does that even mean? It means a dimension can be a decimal. It is as if someone told you that there is a thing that is not fully a line, but not fully a surface either. It is trapped between 2 dimensions, impossible to classify in the old way. And with that, the traditional idea of dimension was shattered. Before this, for thousands of years, human mathematics had treated dimensions as whole numbers, 0, 1, 2, and 3. No one had imagined that a dimension could be 1.26 or 1.58 or any other strange number in between. This problem eventually forced the emergence of a new way of thinking. Felix Hausdorff, one of the founders of topology, realized that the traditional definition of dimension simply could not handle structures of infinite complexity. So he developed a new way to measure dimension. His logic was surprisingly simple. If you divide a line segment into 2 equal parts, you get 2 smaller line segments. If you divide the side length of a square in half, you get 4 smaller squares. If you divide the side length of a cube in half, you get 8 smaller cubes. In other words, dimension is connected to how many smaller copies of the original shape appear when you shrink it. Now apply that idea to the Koch curve. Every time the curve is scaled down to 1/3 of its original size, it becomes 4 smaller copies of itself. Run the calculation, and the result is exactly about 1.26 dimensions. This is not a coincidence. It is a mathematical law hidden deep inside the structure of complexity. Later, people realized that this strange kind of structure was not an isolated case. These shapes shared one common feature. The more you zoom in, the more detail you find. The closer you look, the more hidden structure begins to appear. Ordinary shapes often become smoother, simpler, and less informative when magnified. Fractals do the opposite. The closer you get to them, the more they seem to open up another layer of reality. This feature is called self-similarity. It means that no matter how much you magnify a fractal structure, you can always find smaller parts that resemble the whole. A snowflake, when enlarged, still reveals snowflake-like patterns. A branch on a tree carries smaller branches, and those smaller branches carry even smaller ones. And this feature points to something almost terrifying. In a fractal structure, every part seems to carry a trace of the whole. It is like smashing a mirror into pieces, only to find that every shard still reflects the complete image of you. This is why some scientists began to believe that fractals might be the language the universe uses to write its own source code. But it gets even stranger. This structure does not exist only on mathematical paper. It seeps into every corner of the world, including your own body. Look at the bronchial tubes in your lungs. They split into 2, then 4, then keep branching again and again for roughly 23 generations, eventually forming the tiny air sacs known as alveoli. The total surface area of these alveoli is roughly comparable to half a tennis court. Your body is only so large, yet fractal structure has almost folded half a tennis court's worth of surface area into your chest. Your blood vessels work in much the same way. They branch again and again, forming a network whose total length exceeds 100,000 kilometers, long enough to circle the Earth 2.5 times. This is why fractals are so suited to living systems. A living body has limited space, but the tasks it must perform are extraordinarily complex. The lungs must maximize the surface area for gas exchange inside the chest. Blood vessels must deliver oxygen and nutrients to the farthest corners of the body. The nervous system must build an enormous web of connections within a confined space. Simple straight lines and pipes could never achieve this. Only branching structures can push limited space to its extreme. Nature never wastes effort. Its choice of fractals is no accident. In a finite space, no structure understands how to fill the world better than branching upon branching. And the influence of fractals on life goes far deeper than you might imagine. From the smallest single-celled organisms to blue whales weighing more than 150 tons, across 27 orders of magnitude, their basal metabolic rates all scale with body mass to the power of 3/4. This rule is known as Kleiber's law. After biologists discovered it, they spent decades unable to explain why the exponent was 3/4 instead of 2/3. It was only when researchers approached the problem from the perspective of fractals that an answer began to emerge. The secret seemed to lie in the fractal network of blood vessels inside 3-dimensional space. This network naturally raises the effective dimension of a living body from 3 to something close to 4. That extra quarter of a dimension is exactly what shifts the exponent from 2/3 to 3/4. And perhaps this is where the truly unsettling part begins. A fractal is not just a specific pattern. It is more like a hidden command buried behind all things. From snowflakes to tree branches, from alveoli to blood vessels, from rivers to lightning, nature seems to be repeating the same language again and again. What looks like chaos may have rules behind it. What looks like randomness may hide order deep within. An elephant and a mouse may look completely different, but inside their bodies, they may be following the same fractal law. So the next time you look at a snowflake, a tree, a river, or even the winding veins on the back of your own hand, you may not be looking merely at a shape in nature. You may be looking at the same formula being written again and again by the universe, across different scales.